Okay, can you hear me? Hello.
Hello.
Wow, this is bad. Hello, can you hear me?
Yes, sir, there is an echo.
Is it still there?
No, now it's fine.
No, good. It's not there anymore. Yes. So what I'm doing now is using the iPad to show you the slides. I see that you can see the slides, right? Okay, so since some people said, oh, I have to start, it's recording, it's fine. Yes, so last time, some people said that I was going too fast. So I've decided to review the last 4 lectures today. So we will go through the same material again. In case you have any doubts, they'll get clarified. And if you have any questions, you're always welcome to ask. Okay, so let me begin. I'm going to use this pen now, and let's see if this works. So this works, right? Yes. So what we are going to do is to fix a prime number P throughout this course. And for us, ZP is the ring of p-adic integers, denoted by ZP, of course, and by definition is the limit of these rings Z modulo P to the NZ. They form an inverse system, and ZP is the limit of this inverse system. Here's the inverse system. Of course, Z modulo PZ is our usual finite field FP. These other rings are not fields. Okay, so this ZP is a certain subring of this product ring. And what does a typical element of ZP look like? It looks like this by definition. It's a sequence xn for n greater than 1, where each xn is in Z modulo P to the nz, and xn plus 1 is congruent to xn modulo P to the n. What this means is that the map, so another way of writing this congruence, understanding this congruence is that I have this map from Z modulo P to the n plus 1z to Z modulo P to the nz. I have the element xn plus 1 here, the element xn here. This element should go to this element xn under this map here. These rings come with natural maps, reduction modulo P to the n, and that's what this congruence here says. So that's one way of thinking of a p-adic integer. A p-adic integer, right? P-adic numbers are things which we will come to a little later at the end of this lecture. So there's a bijection of this set ZP with this set consisting of all p-adic expansions. So elements of this set are, of course, B0, the image of 0, B1, B2, B3, and so on, where these BI are sort of between 0 and P minus 1. Okay, so I have a natural bijection of this set 0P with Z mod PZ, 0P squared with Z mod PZ, P squared Z. What is that? This is, if I have B0 comma B1 here, then I can look at B0 plus B1 times P, and this has an image in Z modulo P squared Z. And of course, this diagram commutes because under this map, this B0 will go to B0 and so on. Similarly, I have this map from here to here. It's a map B0, B1, B2 goes to B0, comma B1. And here it goes to the image of, sorry, is there some I'm looking at the chat now to see if, no, everything is fine. So B0, B1, B2, it goes to the element B0 plus B1 times P plus B2 times P squared in this ring. Okay, so of course this diagram also commutes. So what I've got here is the inverse system defining ZP at the bottom, and this other inverse system, which is just an inverse system of sets. The inverse limit of this inverse system of sets is, of course, this object here. So I get, in the limit, I get an object, I get a bijection of these p-adic expansions with the set of p-adic integers. And this bijection is such that the p-adic expansion B0, B1, B2, etc. is taken to the element xn, where xn is the image of this in modulo p to the n. This is an n. So that's exactly what we were saying here. So that's another way of understanding what a p-adic integer is. You can just think of it as an infinite sequence of digits, or you can just think of it as a formal expression B0 plus B1p plus B2p squared, and so on, where these bi's are in 0 to p minus 1. So that's another way of thinking of a p-adic integer. Of course, by the very definition of ZP, you have these maps pi j from ZP to Z modulo p to the j z. These are homomorphisms of rings. Each of them is surjective. And one checks that the kernel of this pi j is the ideal generated by p to the j. In other words, Z modulo p to the jz, which is the thing here, that's also equal to Zp modulo p to the j zp. Okay? So as far as these quotients are concerned, we don't get anything new, but this Zp is very different from Z, of course, because, for example, 1 plus p squared, and so on, that's an element of Zp. It's not an element of Z, right? Okay, so one of the first things we proved about p-adic integers is that a p-adic integer is invertible if and only if it is not in this ideal generated by p. And of course, not being in this ideal is the same as saying that its image in Z modulo pz. See, pi1 was the map from Zp to Z modulo pz. Of course, nobody should confuse Zp with Z modulo pz. Zp is very different from this finite field. Anyway, so let's, just as an example, look at this element 1 minus p. It's in Zp star because what is it? Modulo p? Modulo p, it's equal to 1. So modulo p, it's not 0, and therefore it has to be invertible. And in fact, you can check that its inverse is this element here. 1 minus p inverse is 1 plus p squared plus p cubed, and so on. Okay. So every non-zero p-adic integer can be uniquely written as a power of p times a unit. Of course, that power, sorry, this should not be a z here. This should be an n here. So this little m is a natural number, and for me, of course, natural numbers are why is it not n? So n is equal to 0, 1, 2, and so on. I include 0, as do most people. So every periodic integer, non-zero, can be uniquely written as a product of a power of p times a unit. So if you have heard this terminology, this amounts to saying that p is the only irreducible element in this integral ring Zp. In integral rings, or anyway, so you have this notion of an irreducible element, and p is the only irreducible element in this ring Zp. So this ring is integral, and the only ideals of this ring are, of course, the zero ideal and p to the m Zp, the ideals generated by various powers of p, including m equal to 0, where p to the m, of course, is going to be equal to 1 if m is equal to 0, and therefore then p to the m Zp is just going to be equal to Zp. So that's one extreme. The other extreme is 0, and in between you have all positive powers of p. Okay, so if you now define the Vp of an element of Zp to be m, if x is not 0, and if m is the exponent when you write x as a power of p times a unit, so that exponent here is going to be the periodic valuation of x. And if x is equal to 0, you call it plus infinity. So Vp is therefore a map from Zp to n union plus infinity. Okay, and n union plus infinity it's not just a set, but it's an additive monoid, meaning you can add any two elements of this this set. So for example, m plus infinity is equal to plus infinity for all m in n union plus infinity. So that's how you add elements of this union. And it's a monoid because, right, for a monoid, what do you need? I mean, everybody, so for a monoid, you just need it to be associative and unital, right? So it's associative and unital because it has a 0. That's right. Okay, so it's a monoid, and what this Vp is a map from. This is also, of course, Zp being a ring. It's a monoid. In fact, it's a group under addition, but it's also a monoid under multiplication. So this Vp is a homomorphism of this multiplicative monoid into this additive monoid. What this means is that Vp of xy is Vp of x plus Vp of y for all xy in Zp. Okay. So that's the periodic valuation. This is called the periodic valuation. This Vp. And this allows us to define the periodic absolute value. The periodic is the periodic absolute value. For a periodic integer x, the periodic absolute value is p raised to the power minus Vp of x. And with the convention that when Vp of x is plus infinity, this power is equal to 0. P to the power minus infinity is 0 by convention. Now, yes, somebody had asked at some point whether we could take some other integer or some other real number, let's say 0, c less than 1, can we take some such number instead of 1 over p? And the answer is yes. We can just take, if you have to know the notion of equivalence of absolute values, and then you can take any other number, any other constant c, and you'll get an absolute value on zp, which is going to be equivalent to this one. So this absolute value is, of course, a map. This periodic absolute value is a map from zp to the set of positive real numbers. The positive real numbers are also a monoid under multiplication, because you can multiply any two elements of this set and get in another element of the same set. And that multiplication is associative, and it has a unit, which is 1, the number 1. And so this is a homomorphism. This periodic absolute value is a morphism from this multiplicative monoid to this multiplicative monoid. So that just means that the periodic absolute value of the product xy is the product of the absolute values. So that follows easily from the corresponding result for the valuations, which is over here, right? And the important property of this periodic valuation is this, that the valuation of a sum is at least the valuation, the smaller of the two valuations. It's at least this one. It's greater than or equal to the infimum of these two valuations. So that has the consequence that the periodic absolute value of x plus y is less than or equal to the sup of the two absolute values. And this, these are not just inequalities, they're actually equalities if the two valuations here are different. Similarly, if the two absolute values here are different, you have equality here. So that's what I've, here is an example. If you take the absolute value, periodic absolute value of 1 plus p, it's the same as the periodic absolute value of 1, which is 1. Because the periodic absolute value of 1 is 1, and the periodic absolute value of p is 1 upon p, right? Okay. So now this absolute value allows you to define the periodic distance between any two periodic integers. You just take the absolute value of the difference of those two integers. And it's a distance in the sense that it satisfies this triangular inequality. And it's stronger than the triangular inequality, right? For a normal distance, the triangular inequality says that the distance from x to z is distance from x to y plus the distance from y to z, right? Here, you don't even have to take the sum. You just say the distance from x to z is smaller than whichever of these two distances is bigger. So a fortiori, it's smaller than their sum, of course. You're saying it's smaller than which of these two things is bigger. So one of the properties of ZP is that it's complete for this distance. Okay. And so here's a third way ZP could have been defined. How? We could have simply defined this VP on Z. Then that would give you an absolute value on Z, and that will give you a distance on Z. So that makes it into a matrix space, and you know how to complete a matrix space, right? I presume, or if you know it, then that would be a third way of defining ZP as the completion of Z for the distance dP. What are the other two ways? The other two ways are, the first one is, of course, the definition as the projective limit. And the second one is using just these p-adic expansions. So you identify a p-adic integer with its p-adic expansion, which is some such thing going on forever, right? Okay. So now, and so ZP is the completion, or is complete for this distance. And the subset N in ZP is dense, is a dense subset. For in a topological space, you have this notion of a dense subset. It's a subset whose closure is equal to the whole space. Sometimes it's called everywhere dense. So this subset N is everywhere dense in ZP. Okay. Now we come to an important lemma, very basic because it's used all the time. It's called Hensel's lemma. And what does it say? It says you start with a polynomial with coefficients in ZP. And you start with some p-adic integer x0. Then, of course, you can evaluate the polynomial at x0, and you can evaluate its derivative at x0. And these two things will have some p-adic valuations m and delta. So the only hypothesis we are making is that this m is strictly greater than twice delta. That's the hypothesis. If this happens, then there exists a unique psi in ZP, which is a root of this polynomial, and that doesn't make it unique because you can have many roots of the same polynomial in ZP, right? But if you impose this condition that psi should be congruent to x0 modulo p to the m minus delta, then this psi is unique. There's a unique root psi of f in ZP, which is congruent to the given x0 modulo p to the m minus delta, right? So that is, and moreover, I mean, this is an additional thing you get. The p-adic valuation of the derivative at that psi of is equal to delta. It continues to be delta, which is delta was the thing for VP of f prime of x0, and VP of f prime of psi continues to be the equal to this same delta. Okay, so that's an important thing. We'll use it a number of times to determine what are the squares in QP and what are the roots of unity in QP and so on. For various things, you will need this lemma. Okay, so here is a brief excursion into pure group theory, right? So this doesn't have any arithmetic. I mean, it's just a general thing. So you take a group G, and I'm just introducing some terminology. You'll learn it. So a homomorphism from this group G into the group C star is called a character of G. Just a homomorphism from G into this multiplicative group C star. So sometimes you have some other field, but let's stick to C, the field C of complex numbers. And a homomorphism from G to C star is called a character of G. Of course, you have the trivial character. Then there are these quadratic characters. These are quadratic characters. So these are the ones whose image consists of plus minus 1. Plus minus 1 is a subgroup of C star. And if the image of your character, let's call it chi, if image chi is equal to plus 1 and minus 1, the set, then you call it a quadratic character. Quadratic because it's of order 2. These are the two elements which are killed by 2 in C star. So a quadratic character is one which is of order 2 in this sense that its image consists of plus 1 and minus 1. So in order to understand this concept, it's not a deep or difficult concept at all. You can try to figure out what are the quadratic characters of a cyclic group. Or if you take a product of 2 cyclic groups, what are the quadratic characters? Now, and you can also, this is a small result, which says that if you have a finite commutative group, which is killed by 2, so that's the same as saying that it's a vector space over F2. So finite F2 space. If you have such a thing, then it's determined by the set of quadratic characters of this group. So basically, what a quadratic character does, you have a group G. You can abelianize to get a group, let's say A. And from A, you can do A modulo 2A, which is an F2 space. So this quotient, of course, does not determine G at all. But this quotient is, knowing this quotient is equivalent to sort of knowing the quadratic characters of G. Right? Because every quadratic character will factor through this. And if this is finite, then there's this thing called the duality for finite commutative groups, which determines this in terms of the quadratic characters. So basically, understanding a group, a finite group killed by 2 is the same as understanding its characters. So let's determine the quadratic characters of ZP star. And for that, I begin with FP star. FP star is a cyclic of order P minus 1, right? This, I hope everybody knows. This is cyclic of order P minus 1, which is even. P minus 1 is even. So it has a quadratic character, a unique quadratic character. That's lambda P. Very explicitly, what is it? It sends X to plus 1 if X is a square in FP star, and it sends it to minus 1 if X is not a square in FP star. Okay. Sometimes this quadratic character lambda P is called the Legendre symbol. You might have, those who have taken an elementary course in number theory will recognize this, and it's written, what I would write lambda P of X is sometimes written by other people as XP, the Legendre symbol, like this. Okay, so when is lambda P of X equal to 1? Okay, so this is just recalling some terminology for the benefit of those people who have taken a course in number theory. So saying that lambda P of X is equal to 1 is the same as saying that X is a quadratic residue. And saying that lambda P of X is minus 1 is the same as saying that X is not a quadratic residue, it's a quadratic non-residue. Okay, good. So of course, I have this lambda P here from FP star to Z star, and I have a map from ZP star to FP star. So I can take the composite from ZP star to Z star, and that composite, I'll continue to call it lambda P. Okay, so I've got hold of one quadratic character of ZP star. Okay, so here is a small observation which assumes that even to define lambda p, we had assumed that p is different from 2, right? I mean, for p equal to 2, this lambda p doesn't make sense. F2 star is trivial and therefore doesn't have any quadratic characters. Okay, so if p is different from 2, and if you have a unit u, it's a square. Square means that it belongs to ZP star squares. This is not ZP cross times ZP cross. It's the set of x squared such that x is in ZP star. Okay, so u is a square in ZP star if and only if lambda p of u is +1, which is of course the same as saying that u bar is a square in FP star. Is what I had sometimes denoted pi1 of u, right? Pi1 is the map from ZP to FP. It will take ZP star to FP star, and so after you have used this pi1 for some time, you abandon this notation and you just say it's the map x goes to x bar. So let's come back to the statement. U is a unit is a square if and only if lambda p of that u is equal to +1. And by the definition of lambda p, that's the same as saying that u bar is a square in FP star. Now, the analog of this, it's not analog, it's the same statement. I mean, it's just a translation. It says that ZP star modulo squares is really the same thing as FP star modulo squares. Same thing, meaning there's a map pi1 or induced by pi1, which is an isomorphism between these two things. So let me just recall that ZP star is actually an uncountable group, right? We haven't seen why it's uncountable. We have seen why ZP is uncountable, and we'll soon see that, you know, ZP star has a subgroup U1, which is isomorphic to ZP, and therefore ZP star is going to be uncountable once we have established these things. But I'm saying it right now in order to tell you that although ZP star might be a very complicated, a huge group, this quotient modulo squares is as simple as FP star modulo squares. And it consists of just two elements, one bar and U bar, where you have to choose U to be any element which is not a square. Okay, you have to choose U to be any element which is not a square, right? Okay, that's what happens when P is different from 2. And let's see what happens for P equal to 2. And you expect things to be slightly more complicated for P equal to 2 because we are looking at squares, and squares involves 2 here. So when P is different from 2, this 2 and this P are sort of orthogonal to each other. They don't share too many properties, so not too many interesting, I mean, things don't get complicated. Whereas for Q2, when you are looking at squares in Q2, I have not yet introduced. So Z2, the 2 in Z2 and the 2 here in the squares, they are the same 2. And squares, therefore, in Z2 more complicated. easily compute is just this group consisting of +1 and -1. So there's a natural isomorphism between this group and this group. And again, I'll call it lambda 4. And so lambda 4 is a quadratic group of order 4. Order 4. Inside this, you have a subgroup of order 2. So the whole thing is of order 2. And any two groups of order 2 are canonically isomorphic, right? There's no need to choose an isomorphism. There's only one isomorphism between any two groups of order 2. And so that, in sum, I get a quadratic character lambda 8 plus of Z mod 8Z star. This is a quadratic character of Z mod 8Z star. How do I evaluate lambda 8 plus on an element X of Z mod 8Z star? You first take its image in Z mod 8Z star modulo Z star. So you forget about the sign, plus minus. And then this is a group of order 2. So you have a unique isomorphism with Z star, and that's how you get your quadratic character. So now I have this lambda 4, lambda 8 plus. They are defined on Z modulo 4Z star and Z mod 8Z star respectively. But I can now compose with this projection from Z2 star and get two quadratic characters of Z2 star now. Okay. Right? So I've got now two quadratic characters of Z2 star, namely lambda 4 and lambda 8 plus. And of course, they give me a third one. Whenever you have two quadratic characters, you get a third quadratic character of Z2 star. Namely, you just multiply these two. Just as whenever you have two elements of order 2 in a group, their sum, I mean, it's a commutative group. Their sum is also an element of order 2. Okay, so we had given earlier a criterion for a unit in Z to be a square, and here's the analogous thing for Z2. So a unit U in Z2 is a square if and only if lambda 4 of U is equal to 1 and lambda 8 plus of U is also equal to 1. And these two conditions turn out to be equivalent to U being congruent to 1 modulo 8. And of course, if you recall this notation pi 3, then this just means that pi 3 of U is equal to 1. So that's just another way of saying the same thing. We are not. What needs to be proved is that it's a square if and only if it's congruent to 1 modulo 8. That needs to be proved. And how are you going to prove it? You apply Hensel's lemma with the polynomial with f equal to t squared minus, so what is it called, u, and you take any x naught. For example, you could take x naught equal to 1. Then what is f prime going to be? It's going to be 2u, and you can find out what m and delta are, and if your condition m is strictly greater than 2 delta is satisfied, then you can apply Hensel's lemma to get a square root of u. Okay. So what that means is that Yes. Z2 star modulo squares is really the same as Z modulo 8Z star. And the natural map induced by pi 3 is the isomorphism between these two groups. And this group is generated by just these two elements, -1, the image of -1 and the image of -3. So in all, it has just 4 elements, namely 1, -1, -3, and 3. That's all. So it's a very small group. Although Z2 star itself is huge as far as the cardinality is concerned, because it has the power of the continuum. Okay. So that's, I'm going to go on to something different now. So there are no questions here. Shall I wait for a few minutes to see if somebody has any questions? I'll wait for 2 minutes. Okay. So now we come to a slightly different thing. We have determined what the squares in ZP are, and now we want to see a little better what the structure of the group ZP star is. We have just determined the squares in this group, but we want to now determine the structure of this group. Okay, so let's start. So you define R to be the set of roots of this polynomial, t to the p minus t. This polynomial has many roots. 0 is an obvious root. So R is the set of all roots of this polynomial. And the assertion is that when I reduce these elements of R modulo P, then I get a bijection, namely the map pi1 restricted to R is a bijection onto FP. Okay, so this is something that we had proved, and I'll call the reciprocal bijection to be omega. So that's a map from FP to ZP. It takes an A in FP to omega A in ZP. And what property does omega A have? Omega A has the property that omega A to the power P is equal to omega A, and omega A, when you reduce it modulo P, sorry, it's not P, of course. Omega A is congruent to A modulo P. So there's a unique such element, right? So unique for what? For this property and this property makes it unique. Okay, so omega is this reciprocal map, and it's multiplicative in the sense that omega of xy is omega x times omega y. So of course you have to check first that omega x, if omega x and omega y are in R, then omega x times omega y is also in R. In other words, what you have to check is that this set R is stable under multiplication. I mean, that should be clear just from this. Okay, so as I said, 0 is always a root. Let's denote by R star the set of non-zero roots of t to the p minus t, which is the same as saying that it's a set of roots of t to the p minus 1. The set of roots of this in Zp. And what we have seen is that there are p minus 1 elements in R star, right? That's because there are p elements in R, and I'm just removing one element, so I get in R star there's just one element less, so there are p minus 1 elements. So, and in fact, because this omega is an isomorphism, R star is a cyclic group of order p minus 1. And in fact, this pi 1 is an isomorphism, right? So pi 1 from R star to Fp star is an isomorphism. There are different subgroups, huh? There are different groups. They're not, in the sense that this is a subset of Zp, and this is not a subset of Zp. I mean, it's a subset of a quotient of Zp. So they should not be, they're canonically isomorphic. That's what you should say. They're not the same. Anyway, so what we have got is, yeah, here, let's look at this exact sequence. I've got Zp star, and pi 1 is a surjection onto Fp star, and I've got this omega, which is a section. And I call U1 the kernel of this exact sequence. So U1 consists of what? U1 is the set of all 1 plus AP, where A is in Zp. That's what it is. Is it a subgroup of Zp star? That's because any such element is invertible because it's congruent to 1 modulo P. It's modulo P, it's invertible. So it's invertible in Zp. And the product of any two such elements is again of the same form. So it's a subgroup of Zp star. And actually, you don't have to say all this because U1 is really the kernel of pi 1, and therefore it's a subgroup. And the claim is that this Zp star is actually the product of these two subgroups. So basically, we wanted to understand what the structure of the group Zp star is. Now we understand one of the factors R star, and the other factor U1 is what we want to understand later. So what is the structure of U1? But once you know what U1 is, you have completely determined the structure of Zp star. It is just the product of these two groups. What is an easy example of a product? For example, I mean, C star has two subgroups. One of them is R star plus, and the other one is, I'll call it U, like this. This is R, this you understand what it is. And this is, because this consists of all Z in C or C star, such that mod Z is equal to 1. It's the circle group. And C star is the product R star plus times this U. It's the product of these two groups, right? So similarly, this Zp star is the product of this U1 and R star. R star is finite, cyclic of order p minus 1, and U1 is what we are going to determine. What is U1 like? What is it? What is the structure of this group? Okay. So actually U1 doesn't come alone. It comes with a sequence of decreasing sequence of subgroups, where this Uj is the kernel of pi j. And it consists of all elements of the form 1 plus a times p to the j, where a is in Zp. That's what Uj is. Now, the first observation about these UNs is about this sequence. So, such a decreasing sequence is called a filtration, right? A filtration is just a sequence of subgroups. It's called a decreasing filtration because the sequence is decreasing with the index. The index, when the higher the index, the smaller the group. So it's decreasing. And when you want to understand a filtration, you might want to find out what the successive quotients are. What is UN modulo UN plus 1? So here's the answer. It's actually just isomorphic to FP. And what is the isomorphism? From UN, you have a map to FP, which is what every element of UN looks like 1 plus p to the n times x, where x is in Zp. But that's how UN is defined. It's the kernel of pi j, so its elements are of this kind. So he sent this element to pi 1 of this x. Pi 1 of any x in Zp is, of course, an element of Fp. So you've got a map from UN to Fp. And of course, if x is in, or if this element is in UN plus 1, then this pi 1 of x is going to be 0. In other words, this map induces an isomorphism from UN modulo UN plus 1 to Fp. Okay, so we know what the successive quotients are. They are just cyclic groups of order p. That's one thing. But that doesn't tell you everything about the group. For example, what is UN modulo? Okay, so this is, okay, we'll come to that later. So here is a small intermediate thing which we want to show, that if x is in UN, then x to the power p is going to be in UN plus 1. Okay, and if x is not in the subgroup UN plus 1, then x to the power p is not in this UN plus 2. So that requires proof, and the proof uses the fact that Vp of these binomial coefficients pi is equal to 1, meaning p divides, or these pi are congruent to 0 mod p. Also, and of course, it uses the binomial theorem, but nothing more complicated than this. So now this here says that this raised into the power p maps UN to UN plus 1. Of course, from UN, I can also go to the quotient UN modulo UN plus 1. And from UN plus 1, I can go to the quotient UN plus 1 modulo UN plus 2. And I have an induced map here. And this is an isomorphism of groups. Okay. So, yeah. So that's one thing. And now let's determine what these quotients are. UN modulo UN plus R. Okay. So you take any n to be strictly positive if p is odd and take n to be strictly greater than 1 if p is equal to 2. And for every r, you have the assertion that un modulo un plus 1, un plus r is cyclic of order p to the r. Okay? So how do, I mean, we have proved this already. We know that the order of this group is equal to p to the r, and we had produced a generator, an element of order exactly p to the r, and therefore it is cyclic of order p to the r. Okay, so what does that imply? It implies that if I have an element x in un, and if I denote by xr its image in un modulo un plus r, so fix your n and r and x also, let's say. So you're fixing x, n, and r. Then I'm saying there's a unique homomorphism from z modulo p to the rz to un modulo un plus r, sending this one to xr. This is, I'm not saying anything which you do not know, because all I'm saying is that if I have a cyclic group of order p to the r and an element xr in that cyclic group, there's a unique map from the standard cyclic group z modulo p to the r, sending 1 to that element. And what does it send? An arbitrary element a of z modulo p to the r z. It sends it to xr to the power r, to the power a. Or I could have written z here instead of z modulo p to the r z, right? So there's a unique map from z to un modulo un plus r, sending 1 to xr, and it sends a to xr to the power a. If you are more comfortable with this, yeah, but I think it's better to think of it as a map from x modulo z modulo p to the rz, because then I want to compare it. So I have, this is the map I've constructed. Suppose I have now an element x in un, and xr is the image in un modulo un plus r, and xr plus 1 is the image in un modulo un plus r plus 1. Then I'll have a map fr and a map fr plus 1. And obviously this square will commute, right? Okay. And I can now think of each of these modules as a ZP module. They are basic. You would say, no, they are Z modulo P to the N Z modules, but this itself is a quotient of ZP. So every module over this can be thought of as a ZP module. So I think of all this as a projective system of ZP modules. This here as a projective system of ZP modules. And in the limit, what I'll get is a map from ZP to UN. Remember what we have fixed are N and X in UN. So I'll get a map from ZP to UN, sending 1 to X, and then it sends A to X to the A. Now you might ask, what is X to the A for an element A of ZP? Yeah. So the answer is, okay, here is one answer. Here's one answer. So after all, your A, which is an element of ZP, is a sequence like this: AR, R greater than or equal to 1, where each AR in Z modulo is in Z modulo P to the RZ. And your X, which is an element of UN, is also a sequence of elements like this, u xr, which is an un modulo un plus r. So x to the a, the meaning of x to the a is the sequence x to the xr to the power ar. Xr to the power ar, and these things make sense because that's what we have defined here. Xr to the power a. I mean, here it was not being called ar. I could have said ar goes to xr ar. Okay, so that's how the upshot is that each un is a ZP module. Because this is an isomorphism, that's what we have proved. And that holds for any n if p is odd, and holds for any n strictly greater than 1 if p is equal to 2. This un is isomorphic to ZP. So this does it for n equal to 1. What does it say? If x is an element in u1, wait a moment. We get an isomorphism. Did I take my x not in to be taking an x which is not in un plus 1, then I get an isomorphism. Otherwise, of course, I don't get an isomorphism here. When I say that you get an isomorphism 1 going to x, this x is something which is in un, but not in un plus 1. Okay, so for n equal to 1 in particular, you get this thing for odd p, that if I take an x in u1 which is not in u2, then there's a unique isomorphism of ZP modules sending 1 to this x, and it sends an arbitrary element a to x to the power a. Similarly, for p equal to 2, here I cannot take n equal to 1. I have to take n at least equal to 2. So if I have an x in u2, which is not in u3, then there's a unique isomorphism of Z2 modules from Z2 to U2, which sends 1 to X. And in general, an A in Z2 is sent to X to the power A. Yeah, X is not in U3. Okay. So that is, so I should have said that, this leads to a complete determinant ZP star. So first we said that it's U1 times R. This R, and this R is really isomorphic, naturally isomorphic to FP star. This is isomorphic to ZP. So if P is different from 2, this is isomorphic to Z. You make a choice here. You have to choose an element in 1, which is U2, and then you get an isomorphism with ZP. So that determines the structure of ZP star when P is odd. So for P equal to 2, the analogous thing is that Z2 star is U2. No, I should have, yeah. So that's, okay, U2 times Z star. So that, of course, consists of plus minus 1. And this U2 star is isomorphic to Z2. Again, you have to choose an isomorphism. In other words, you have to choose an element of Z2, U2, which is not in U3. Okay, so that determines the structure of these groups, Z2 star and ZP star for odd prime spin. Okay. So now we come to the definition of a field QP. It is just obtained by ZP by inverting the element P. It is a field because everything P is the only irreducible element in ZP. Anyway, so what you can easily see is that every non-zero element in QP can be uniquely written as a power of P times a unit. These are the units and this is the power of P. But now you have to allow the power, of course, to be an integer, positive or negative. And the VP that we had here from ZP to N union plus infinity can be extended to a VP, to a map VP from QP to Z union plus infinity by the same method. I mean, VP of an X like this is going to be the exponent M, the power of P appearing in this expression. So this is a morphism of multiplicative monoids, which just means that VP of X times Y is VP of X plus VP of Y. Here, this is being thought of as a multiplicative monoid, and this is being thought of as an additive monoid. And what is additive about it? You just N plus, of course, if is equal to plus infinity for all N in Z union plus, okay. Okay, so there we are. So yeah, this valuation VP, it's called the periodic valuation, right? The fundamental property is that VP of X plus Y is at least equal to the smaller of these two is greater than the inf of VP of X and VP of Y. And you actually have equality if the two valuations are different. Okay, and from this valuation, you can define an absolute value, the periodic absolute value, which is, you just raise P to the power minus VP of X. So now X is any element of VP of QP, and the convention is that P to the power minus infinity is of course equal to 0. So this periodic absolute value satisfies this inequality. It says that the absolute value of a sum is always smaller than whichever of the two absolute values is bigger. And one should also say that your equality, if these two absolute values are different. Okay, so that allows you to define a distance on QP. So X, Y are in QP, the distance, periodic distance dP between X and Y is just the absolute value of the difference of X and Y. And it satisfies this strong form of triangle inequality, which says that the distance from X to Z is always less than the bigger of these two distances, the distance from X to Y and the distance from Y to Z. Okay, so now we've got a distance dP on QP. So QP is a metric space and one can ask for its completion. It turns out that QP is actually already complete. So that one has to check. QP is complete, and you could have defined QP as the completion of Q for this distance dp, right? I mean, you just have, what is this? So I could have defined VP on Q first, and then of course the periodic distance, and then I will define the periodic absolute value and then the periodic at it. And you can complete it and you define QP. So then QP will come with an extension of this VP, which is there on QP. It will, the VP define Q. Then you define this distance dp on Q. You get the completion QP. When you complete a metric space for a distance, the distance extends to the completion, right? And therefore, you'll also get a valuation on QP, and you can define ZP as the set of elements in QP valuation positive. So, oh, okay, I'd already written it here. Anyway, doesn't matter. So, this is the fourth way of defining ZP. Yeah? What I just described, the fourth way. Three ways. The first, which is ZP as the projective limit of this inverse system. The second definition is in terms of periodic expansions. Okay, so these are just formal. You can think just plus B plus B two P and digits below and P. So these are just formal power series in the variable P, so to speak. P is of course not a variable, it's a fixed number, it's a prime number, but just as you have a power series in a variable, you can look at power series, formal power series in P, and any such power series is a periodic integer. And these are all. The third way of defining ZP would be as a completion of Z for this distance dp. How do you get a distance dp on Z? Of course, you have this periodic valuation on Z, you have the absolute value on Z, and therefore you get this periodic distance on Z. And finally, finally for today, because there are even other ways of defining ZP. So, but for today, the fourth way of defining ZP is as a subring of QP consisting of those elements whose periodic valuation is positive. Okay. So we had determined the structure of ZP star. What about QP star? What is the structure of QP star? The group, the multiplicative group of the field QP. So we know that it comes to the valuation VP to Z. So this sequence is exact. The kernel of VP is of course ZP star. And by definition, a uniformizer of QP is any element whose periodic valuation is equal to 1. So maybe I've already said this, that every element X of QP, every non-zero element X of QP can be uniquely written as a power of, okay, earlier I had said it for P, But now you can see that the only role P played was as a uniformizer of QP. If you have P pi here, a power of pi, positive, negative power of pi, times a unit. A unit means an invertible element of ZP and not of QP. Huh? Okay, so well, in other words, the mapping from Z to ZP star to QP star, taking the pair MU to pi to the M times U, is an isomorphism of groups. So if you wanted to understand the structure of QP star, you just need to know what Z is and what ZP star is. You all know what Z is, and ZP star, we have just determined what it is. There are two cases, P equal to 2 and P different from 2. So there are these two cases where the structure is slightly different. But finally, okay, yeah, here it's written. So if P is different from 2, then QP star is Z cross ZP star, and ZP star is FP star times U1, and U1, remember, is isomorphic to ZP. And if P is equal to 2, this should be, okay, we are not yet coming to P equal to 2. We are still in P or. So if this is what QP star looks like, the squares in QP star will look like 2Z times ZP squared. So and that is 2Z FP star squares, and the squares in U1 are equal to U1. U1 squared is equal to U1 because a U1 is a ZP module and 2 is actually invertible in ZP. Okay, so if you have a ring A and an A module M, and if you have an element little a in A, which is invertible, then multiplication by A, let's call it A sub M, that takes X in M to A times X. This is an automorphism of the group. It's a bijection, right? So that's what is being said. 2 is invertible in the ring ZP. Therefore, multiplication by 2, which is actually raising to the power 2. Now, these are multiplicative groups being considered as modules over the ring ZP. So that's raising to the power 2 is a bijection. Everything in U1 is a square. So what's the result of this? It is that QP modulo squares just consists of these 4 elements. 1, U bar, P bar, P bar, U bar. Okay, where U is any element such that it's not a square, which is the same thing as saying that lambda P of U is equal to -1. Similarly, Q2 star modulo squares, you can check that it's equal to, I mean, it just consists of these 8 elements. It's 1, -3, -1, 3, 2, -6, -2, 6. Just these 8 elements in Q2 star modulo Q2 star squares. Here you had 4 elements, here you have 8 elements. So finally, let's determine the quadratic characters of QP star. So, of course, you have this valuation VP from QP star to Z. It sends, I mean, So if x is equal to p to the m times u, then Vp of x is equal to m, right? And this u has to be in Zp star. So this is the valuation. And of course, from Z, you have this map from Z to Z star, the unique quadratic character of Z, so to speak. It sends m to -1 to the power m, right? So I can compose this Vp with this quadratic character to get a quadratic character nu p of Qp star. So nu p of x is basically -1 to the power Vp of x. And this particular quadratic character of Qp is going to be called the unramified quadratic character of Qp. Why? That we will see later. Why is this unramified and the other ones are ramified? All that will come later. So for p different from 2, I have these other quadratic characters. I have another quadratic character, which is you from QP, you have to choose for naming these other quadratic characters, you have to choose a uniformizer. So once you have chosen a uniformizer, you get a map from QP star to ZP star, right? What is that map? It sends X to, what is this here? It sends X to X times pi. So if you choose a uniformizer pi, right? It sends X to X times pi to the power minus Vp of X. So that this is in ZP star. Okay, so I have this map sending X to X times pi to the power minus Vp of X from Qp star to Zp star. And then I can apply this lambda p, which is of course a quadratic character of Zp star, and I'll get a quadratic character lambda p of Qp. Of course, so this depends on the choice of a uniformizer. And the proposition is that the only quadratic characters of Qp are nu p, this unramified quadratic character which I defined here, lambda p, which I've just defined with the help of a uniformizer, and the product of these two things. These are the only quadratic characters of Qp star, one should say, not Qp, of course. Okay, so, and here's a small matrix giving the values of these quadratic characters, lambda mu p and lambda p, on the two elements which sort of generate Qp star modulo squares. That's what we had, right? Qp star modulo squares is something generated by by u bar and p bar. U and p generate this quotient. So what are the values of these two quadratic characters on these two elements? These are the two quadratic characters, these are the two elements, and the values are 1, -1, -1, 1. And the same thing we have to do for Q2. So here this P should be 2. So we have Q2 star squares. We choose, here we have to choose a uniformizer. I mean, we could take 2 as a uniformizer. So if you choose a uniformizer, you get a map homomorphism from QP star to Z2 star, Q2 star to Z2 star. And from on Z2 star, we have defined these two quadratic characters, lambda 4 and lambda 8 plus. And here is the list of all quadratic characters of Q2. The only Q2 star, the only quadratic characters of Q2 star are nu to the unramified quadratic character, lambda 4, lambda 8 plus. So lambda 4, lambda 4 and lambda 8 plus have been defined here as a composite. So you have these three. And in the case of odd p, essentially, no, forget about odd p. Let's stick to p equal to 2. So you have these new two, the unidentified quadratic character, lambda 4, lambda 8 plus. And then the others, which are sort of products of various combinations of these two, these three. So these three are in some sense the basic quadratic characters, and the others are just the product of nu 2 and lambda 4, nu 2 and lambda 8 plus, lambda 4 and lambda 8 plus, and the product of all three, nu 2, lambda 4, lambda 8 plus. So basically you have these three basic quadratic characters, and you have these three elements which generate Q2 star modulo Q2 star squares. These three elements generate this group. It's a group of order 8, and these three elements sort of constitute a basis over F2. Anyway, so here are the values of these three quadratic characters on these three basic elements. So this is the matrix. And I believe that this is all we had done in the first 4 lectures. Of course, we had proved all these things, but for those who had not been able to attend or follow what we had done in the previous 4 lectures, should now be in a position to follow the remaining course. So are there any questions? Hello, any? Yeah, are there any questions? Okay. If not, I'll stop.